Okay, hello. This is the slide deck that we've posted on structs and strings. So unfortunately do not have time in lab to go over them, but it should prove helpful on project 4, which is why we are posting this content now. Yeah. Okay, just to start off with string declarations, this is some content that should have been on the previous homework. So ideally you would already know how to do all this stuff, but we're just going to go over it anyways. So when you declare a string using the char star notation, it's going to create an immutable string literal that's stored in read-only memory, and the variable that you have is a pointer to that string. And now, important things to know are that you can move the pointer, but you can't edit the value of the string itself, right? So you can see here that we can increment the value of a, right? So if we were iterating in a loop, we would be able to read through each individual character of the string by just using a plus plus, right? But you can't actually edit the value in the string, or in this case, it would be in a specific address within the string, right? So in this case, after we do the a plus plus, we would end up at character e. But if we wanted to change that second character to some, we wouldn't be able to do that because this string literal is in read-only memory and we can't modify it. Just another note, with any string that we declare, the null terminator will always be appended at the end of the string. So in this one, we have hello, which is 5 letters, but then because we have the null terminator as well, this is going to take up 6 memory spaces. And this is going to be the same regardless of how we define the string. Oh, this is wrong. This is supposed to be char array. Please excuse my handwriting with my mouse here. So the second way you can declare a string, besides using the char pointer with string literals, is storing a mutable character array. And when we do this, the pointer that we have is going to be a constant pointer to the array. And what this means is the abilities we have are essentially flipped from the character pointer. So in this case, we can't move the pointer, but we can edit the value that's in the array, right? So we can't do this b++ to move our pointer through the array, but we can set the value at a certain index to a different value. We talked about this in previous labs, I believe. So in this case, if we wanted to do something similar to this, where we're incrementing a pointer, we would have to declare another pointer using the other notation, like character asterisk pb equals b. And then we'd be able to use that with the increment. But as it stands, we can't use b itself because it's been declared as a constant pointer with this array notation. A second note on the what size of returns with these different declarations. When we use the character pointer, it's going to return the size of the pointer itself because, well, a is C just sees a as a pointer to a single character and doesn't know that it's part of a larger string. While if we pass in the array notation, it's going to give us the total memory occupied by the array like it does for any other kind of array. And yeah, there was a question about this on the homework, so hopefully you know how to do that already. All right, so just a bit of a practice problem with that. Let's say Henry learned there are 2 ways to declare a string, but his code here is not compiling. I was surprised we put Henry in the slides, considering he's not with us anymore. Rest in peace. No, he's just a 4290 TA now, but yeah. Anyways, once again, this is essentially exactly what the question from the homework was. Which lines in the code will result in compile time errors, right? So if we recall the abilities we have with declaring these different types of strings with the array notation, we can increment, or I mean, sorry, because it's a constant pointer, we can't increment or decrement it, we can't change its value, but we can change what values are stored within the character array itself, because this is going to be just mutable values that are stored on the stack. As opposed to when we use this pointer notation, we can change the value of the pointer by like incrementing it, decrementing it, but we cannot change the value of the actual string because that is a string literal stored in the read-only memory. So with that in mind, we see that the errors that occur here, first, we can see here we're trying to change the value stored at b, but because that's a string literal, we can't do this, right? We can't dereference value b and set it to something else. This is invalid. and will result in a compile time error. And the second error along similar lines is that because a is a constant pointer, we cannot increment it right here. So yeah, you can see that we have here, like we talked about, yeah, if we declare a string using the character pointer, it results in the character array being immutable. This is a bit misleading. I mean, any string is technically a character array, but this the way we've written is a bit confusing. But yeah, because it's a string literal, it's immutable, so this one causes an error. And like we said, anytime that we use this constant array pointer and try to change that, it's not going to work. All right, moving on to structs. That should be everything you need to know about strings and the difference in the ways to declare them. So we're going to talk about structs now. And these are essentially data structures that are used to group multiple different elements together. And the key thing about these structs is that they can group elements of different types, right? And this is important. You can see here in this struct right here, we have like an int and a character. And a pretty simple analogy can be made between structs and like objects in Java. Like an object can have attributes of different types. Similarly, structs store different elements of varying types, right? And there are a couple of different ways to access elements within a struct. Well, I guess it's technically only one way, but depending on whether you have in a direct instance of the struct or a pointer to a struct, you access them in different ways. So if you have an instance of the struct directly, like we have right here, you just declare it as a struct itself, you can access that element by using this dot notation. So if we wanted to access value 1, it's like this object instance dot value 1, and that's how you access it in that case. And there's some shorthand for if we have a pointer to a struct, because we'll find that having pointers to structs is often more useful than having the structs themselves. Like maybe we want to pass it to like a function that's going to need to be like passed by reference instead of passed by value if we want to actually modify the value in the struct. In that case, we have a special notation, this arrow notation right here, which is just shorthand for dereferencing the pointer and then using this dot notation. So yeah, this is just a cleaner way to do this. These achieve the same behavior. Yeah, it's just some practice on accessing struct members based on what we just learned. Let's say Rick is tired of having so many students and wants to set the number of students in his lab to 4. And what line would we have to write here to accomplish this? So you can see here that lab1 is just defined as an instance of the struct and not a pointer to it, right? So in this case, we use that dot notation. So lab1 dot num. I'm not going to write out the entire thing because that's annoying. Dot num, and we just set that directly to 4. And then in the second part, Shivani's messed up the lab, so now he only has a pointer to his lab. That's unfortunate. And so how can we update the number now? In this case, we can use the arrow notation with this new pointer. And in this case, it would be pointer or arrow to num equals 4. Right. Yeah. So you can see here this is just an application of like using the dot notation versus the arrow notation. Most important thing to see here is just like this is a pointer. This is an actual struct. Okay, so just matching valid definitions, I suppose. Important info to see here. Now we have lab 1 and lab 2. Lab 1 is an actual lab. Lab 2 is a pointer to a lab. So we know that this one is valid because lab 1 is an actual lab, so we can use the dot notation, but this one is not. And we can see here, in this case, we're treating lab 1, I guess, what is this going to do? I think because this, I don't remember the precedence, but it seems like this will try to dereference whatever value is at num students, which does not work. So this one's just wrong. This one right here, we can see is like the equivalent statement for the arrow notation from before. First, since lab 2 is like a pointer to a lab, we dereference that and then take the number of students, so that one's fine. But this one, once again, I'm not exactly sure what these are doing, but yeah, you can see this wouldn't have the expected behavior. Next, with the arrow notation, like we said, it's just equivalent. Like this statement right here would be equivalent with this. Well, I guess besides the numbers, but this one is fine. But since lab 1 is not a pointer, that would not work correctly for us. So yeah, it's just going to be the direct access with the dot notation, and then for lab 2, because it's a pointer, the arrow and dereferencing, then using the dot notation achieves similar, or they achieve the same behavior. Yeah. Next, this was on the previous slides, but with structs, you can use a typedef, right? Typedef is this command that allows us to define a type and it simplifies instantiations of structs. So what we can see here is we have a type def struct lab, and then we put the type that we want struct labs to be referred to over here. So instead of using struct lab, we can just use lab now because we've written this type def for labs. So in this case, if we want to create an instance of a lab called best lab, we can just directly use best lab like this. And the difference between this and like a regular struct declaration is that a regular struct declaration would just be like struct lab, and then we wouldn't have the type at the end. And to declare that, we would have to write out struct lab and then best lab, which is a bit more inconvenient. So that's why we have type defs, to make this whole process a bit more convenient in terms of using them. So let's match these up now. Essentially what I just said, you can see here, if we don't have the type def, we'll have to use the struct lab. And if we do have the type def, so we can truncate that to just lab, we can use the lab directly. Oh yeah, okay. In the case that we have a type def, the using struct lab will also work. But that kind of defeats the point of having the type def, right? We want to have the type def so we can just type this instead of having to type struct before that. Last thing, I don't really know why we put this in here, but I guess it's important to know as well. Signed versus unsigned ints have different representation ranges, which makes sense because, I mean, if they're signed, you have to use half the range for negative numbers and half the range for positive. But if they're unsigned, you can just use all of it for positive. Yeah, so you can see here, unsigned, all 32 bits for magnitude. If it's signed, the most significant bit will be the sign. What is this? Yeah, 0 is positive, 1 is negative. So, oh yeah, I guess this is important. Even though both types of integers take up like the same memory size, they're going to be interpreted differently. So we could pass in like the same value to, and we could define it as an unsigned int versus a signed int, and they would give different values depending on what you passed in. Yeah, specifically, I think just specifically if the first bit is going to be a 1, because that's the only case in which it would be interpreted as negative. But yeah. Next. Overflow wrapping for unsigned values, it just wraps around to 0, but then for signed integers, it's undefined behavior. Okay, last thing then, just prefix versus postfix, incrementing and decrementing. This is the same as Java and other languages that support this type of operation. If it's prefix, it'll do the operation first and then use the value for the calculation. And if it's postfix, it'll use the value first and then increment it. So, I mean, you can see an example here. In this case, if we're taking this integer x and then assigning a to plus plus x, we're going to add 1 to x first and then assign it to a. So a is going to get 6. In this case, for the postfix, if we do it after, b is going to get 6, and then x is going to become 7 after it's assigned. And yeah, that should be all the content for this slide deck, and hopefully that was helpful for the projects. Yeah.